I'll wait.
Is it a Michael edition?
There will be a Michael edition involved, yes. And we're going to see something else as well will happen
So
here.
condensation.
Yeah, we'll have a condensation also. And when we have both of those, it's got a special term, right? So this will be first a Michael, followed by a condensation, which that altogether is the Robinson, right? So if we're going to go ahead and do the Michael edition first, hopefully we can identify our donor and acceptor. Which one is which? Left molecule, right molecule. Which one's the donor?
The right one?
Right, that's the one that's got our two functional groups on it, two things to stabilize the enolate. So this is our donor, and then, of course, this must be our acceptor. Of course, the acceptor is the one that is alpha-beta unsaturated as well. So, if we're going to go ahead and do our Michael addition first on these, let's go ahead and I'm going to just draw our Michael donor. And we're going to go ahead and deprotonate this. So in the middle here is going to be the best position. That's the most acidic hydrogen. So we're going to go ahead and grab that one. And we can resonate up to either side. Does not matter, since this is symmetrical. Alright, so we've got our enolate. So we know that since this is going to be a Michael addition, we're going to have that enolate is going to attack the fourth position, or the beta carbon of our Michael acceptor. So if we redraw that acceptor, this is the beta position here. That's the one that's going to be attacked. So if we go ahead and draw the arrows, we're going to close down our carbonyl, and then we're going to go ahead and have our enolate attack that beta carbon. That's going to move some things around, and we're going to pop open our aldehyde there. Alright, so this is going to give us a rather vertical molecule, so let's just see what we can do. Alright, and then we've got now 1, 2, 3, 4 carbons. So 1, 2, 3, 4 carbons. We now have, that's not connected to the oxygen, by the way, that's just a methyl group. Alright. And so now what's going to happen with this? What's going to happen next here?
Is there like a intramolecular thing attached?
Yeah, right. So that enolate that we have there now is going to go ahead and attack one of the carbonyls. Since this is symmetrical, it doesn't really matter which one it's going to attack. So we can choose. So our enolate is going to close down, and we're going to go ahead and attack one of these. Either one. Again, it's symmetrical, so it does not matter which. Oops. If that happens, we're going to have a lot of counting to do here. So let's go ahead and see. So we're going to have this carbon here is going to be connected to that carbon. So 1, 2, 3, 4, 5. So this is going to be a 5-membered ring that's connecting carbons 1 and 5 there. So if we kind of redraw, I'm going to start with that cyclohexane part. So we have carbon 5 there, which will be connected to the new carbon 1. So this is carbon 5 right here. So that's going to be connected to carbon 1. So we're going to have a 5-membered ring here. If we redraw those purple bits, that's those carbons there. And so now we just need to put everything on our skeleton that's on those carbons already. That carbonyl, by the way, on the right side is unchanged, so we can keep that there. On carbon 3, on carbon 4, 5, 4, how many? Why do I have 3 and 4 in the same place? This will be a 4-membered ring, actually. Let's double check my counting here. 1, 2, 3, 4. Okay, I lied. 4-membered ring. Alright, so with this, now we can go ahead and make sure that everything's on there properly. So on carbon, I just erased the numbers. On carbon 3 we had a methyl group, so we should still have that there. On carbon 2 we had a methyl group. On carbon 1 is where we're going to have our carbonyl. And in this case it's an aldehyde. And then carbon 4 is where we're going to have our hydroxy. But we know that since this is going to be a condensation reaction, we're going to be forming our double bond in place of this hydroxy. So we can do that now, or we can do that in a second step. That's all right, either way. If we want to do it in a second step, we just need to have our hydroxide come along. It's going to grab that alpha proton, and it's going to kick out the hydroxide. Remember, hydroxide is acceptable as a leaving group for this type of condensation. And so if we go ahead and do that, we're going to now have a double bond there in our 4-membered ring. Those two need to be connected. Everything else stays the same. So we still have a methyl group there, and we have our aldehyde. So, fun. So Robinson, remember, is going to be 2 reactions in sequence. So first a Michael addition, you form an enolate through that Michael addition. That enolate then does an intramolecular aldol condensation. And you're going to end up with a new ring being formed with a double bond in that ring between your alpha carbon and your beta carbon. The beta carbon is going to be where one of your carbonyls used to be in your other compound. All right, so these are the tougher ones because it's 2 reactions at once, right? So let's go ahead and make it big or vertical. All right, Rooney, I'm going to put you down, okay? Come on, buddy. There you go. All right, any questions on this one? Of course, if you attack the other carbonyl, it's the same thing. It's just symmetrical. You just get it on the other side instead. Same molecule, though. All right. Then let's do another one. Let's say we have... What shall we do? Let's do a... This is an interesting problem. I like this one. Okay. Another one. So this problem, we're just going to be determining the reagents necessary to do the following 5 reactions. All right, so remember when we are looking at a synthesis type things, we're just determining the reactants here, or reagents that are going to get us from starting material to product. We want to look at the functionalization of our enolate or our product. So this product is a 1,3 type of functional compound. It's got a functional group at carbon 1 and a functional group at carbon 3. Remember that a 1,3 product is something from an aldol or a claisen, right? Or any of those other variants that we talked about. So which one is going to be the more appropriate one here? An aldol or a claisen? Based on the rest of the functionality here.
Claisen.
This is a claisen, right? And you know that because, of course, we end up with, we have our ketone and we have an ester. That's typical of a claisen condensation. So if we wanted to do a claisen, what are our reagents going to be for this?
NOH and I guess just like H3O or HCl.
NaOH and HCl.
Oh, I meant H3O plus.
Okay, well, still.
Or wait, oh, did I say NaOH? I mean like Na, I guess NaO. I think like ethanol or
ET, yes, I would say
ET.
that's definitely the better choice there. So we're missing a part here, right? We will need a source of the carbons as well. So the sodium methoxide, like that's the base, right? This compound here has no alpha hydrogens, right? Because the left of the carbonyl you have a benzene ring, so there's no protons there. On the right side is an ester, so you have no protons there either. So this has got to be a mixed claisen, because you simply do not have any alpha protons on the left there. So yes, you are definitely going to want to use the ethoxide as your base, absolutely. But we are missing part of our set of reagents here. And we're not going to actually need the acid for this one. So what's the difference in carbons between the starting material and the product? Or like structurally, what's different?
And there's 2 extra carbons.
It's got 2 more carbons, right? So we need a way to add 2 carbons to this thing. And so we need something that has alpha protons and 2 carbons. So we have options. For something with 2 carbons and alpha hydrogens, we have the following 2 options. I mean, we could throw nitriles and nitros in here too, but those don't make any sense because we don't have those in the product. So we have 2 things that are 2 carbons that do have alpha protons. So of those, which of these 2 is going to be more appropriate? Are we going to want an aldehyde here or an ester?
Ester?
It's going to be the ester, right? And we can tell that because we have the ester on the other side of our molecule. So in this case, we're going to want to use the ethyl ester as our carbon source. And so, yes, you'll be putting this in with the sodium ethoxide. If we consider what happens, we have our base come along, grabs this, forms our enolate. Oops, whatever. Guess we're blue now. That enolate is going to attack our starting material. I'll do my arrows in the correct color this time. Opens this up. And I'm going to just draw it on the other side if that's okay. So here's our benzene. We now have this alkoxide. We have the ester. And then now we have our 2 carbons that we've added. And the second one has the ester on it. All right, and then so remember that because in the Claisen, what happens is we just close this down and pop out our leaving group. And in doing so, we reform our carbonyl. And then we just have the rest of it, which is the other 2 carbons with the ester on it. And so we end up with our product. So the set of reagents you're going to put in here would be the sodium ethoxide followed by your ester. And so those would be the reagents necessary. And remember, you kind of want to do this in this order, because if you put the ester with the alpha hydrogens in, and then put the base, you have the chance of it attacking itself. So you always want to have kind of your no alpha hydrogen one present with the base, and then you dropwise will add in your ester that has the alpha protons. So that way you can kind of make sure that you're reacting the correct 2 together. Otherwise you end up having the acetyl ester attack itself. Okay. So, any questions on that one? Yeah.
I have a question. So since we know this was a mixed Claisen, so we don't use the KH or LDA?
You could.
Instead of the first step, we use that?
You could, yes. Although it is typically, because we don't have alpha protons, we are okay to use the ethoxide, so we technically should. KH or LDA will get us there, no problem, right? But since those tend to be the more reactive ones, since in this case we only want to resort to the more reactive ones if we have one of our reagents, or if both of our reagents have alpha protons. Since we have one that does not, remember there's kind of 2 options for a mixed Claisen or Aldol. Option 1 is one reagent has no alpha protons. Option 2, LDA or KH. So, like you could use KH or LDA here, but it's not necessary.
Okay, thank you.
Yeah.
One question. So, since it's the ethanol to the right in the products, we have to use in our reagents we have to use the ethyl ester, right?
Correct. Yeah.
If it was a methyl.
If it was a methyl ester, then yeah, you'd have.
Okay. Same. Okay.
Although you typically want to have it as the same ester as your starting material, because then otherwise with the base you risk it switching itself out. Like if you put the methyl ester in there, some will have the methyl ester in your product, some will have the ethyl ester, because your sodium ethoxide would be able to go transesterification with your product. So it's just best to have everything the same. If you want the methyl ester, I would still use the ethyl ester as your reagent and then do a transesterification afterwards. After this step, then you can do the methanol and acid, and then you'll replace that OET with OME. That would be the way to do that. Otherwise, you end up just with a mix of products, and so always want to avoid that. Okay. All right, let's take this molecule and do more stuff with it. Okay, so now I want this. So, this is an interesting one. How are we going to take this now keto ester and get rid of some of this stuff? How do we remove carbons in this sort of pathway?
Would you do H3O plus and then heat?
Yep, yeah. So you'd hydrolyze it first, right? So you'd hydrolyze it, which forms. Let's. This is the question here, right? So if we take that first part here, if we hydrolyze it, we'll end up with OH, right? And then, absolutely correct, we are going to end up decarboxylating this. Remember, if we can remove CO2 from this by heating it up. So decarboxylation is a great way to remove a single carbon if it's got the carboxylic acid there. We can decarboxylate. So very useful little bit there. Okay, cool. So if we decarboxylate, where did this problem go? I just lost it. We have more to go here. There it is. Okay. Cool. So if we're going to lose our CO2, we're going to end up now with our ketone. So now let's take, so the reagents there are acid and then heat, and we'll end up getting rid of our CO2. Next. Yeah, I'm going to just do it on a separate line. So let's take that acetophenone that we just made, and let's turn it into no, just this. So structurally, what do we have different here?
An extra carbon with a double bond.
One more carbon, and we have a new double bond. Absolutely. So, we're going to need a single source of carbon here, and we're going to need to make that double bond. So, since we have a ketone to start, we can think, how can we add one more carbon to this and then also get a double bond there? And notice this is an alpha-beta unsaturated ketone that we're going to end up making. If we think here we have, well, these are both just hydrogens. If we want to think, how the heck do we make this? This is an aldol condensation, right? Making an alpha-beta unsaturated ketone or aldehyde is from an aldol condensation. So this must have come from using formaldehyde as our that one extra carbon, and we'll just do an aldol using our acetophenone with this aldehyde. formaldehyde. And so this one again is option 1 mixed aldol, so we do not need the LDA or KH here. So we can go ahead and use a milder base. So what we would want to do is put in our aldehyde that has no alpha protons. We will put in our base, and then we will put in our ketone. Ketone will form the enolate. Enolate will attack the and then we'll get our product, and then we'll look at the mechanism in just a sec. So, if we take a look at this, of course, proton gets abstracted by our base, forming the enolate. Alright, so now we have our formaldehyde molecule. This is again a good example of a mixed aldol because we have a ketone and an aldehyde. Remember that aldehydes are more electrophilic, so we have less of a chance of doing an attack to the same compound. So we're more likely to attack our aldehyde. So it's a good thing. Doing this. Now I just have one more carbon. It's going to be an O- technically. And so if we want to heat this up, or I'm sorry, if we want to condense this down, we're going to need acid and heat, right? To get rid of, or base and heat, either way. We just need to finish this thing off. So we can have it just take a proton from the water. If we do that, we have our OH, our hydroxide comes along. We're going to grab that alpha hydrogen and condense by kicking out our hydroxide, and we will end up with our condensed product. And so we have now synthesized our aldol condensation product. Alright, so step 1, NaOH. Step 2, our ketone, and then step 3 would be heating it up. And that'll get rid of our hydroxide, leaving us with the condensation product. Alright, so questions on that one. So this time we were doing a mixed aldol.
For the last step, do we also need heat?
I'm sorry? For which part?
For the last portion, do we also need heat when we?
Yes. So this is where we've got the heat going on this step here. Yeah, for sure. Yes, that'll be our heat. Okay. Next, let's take this compound and now do something else with it. I thought this is a cool problem because it just take the same thing and now do different things to it. Let's go ahead and do this. Okay, yeah. Alright, so we're going to add now, or I'll let you tell me what we're doing. So what's happening in this one?
Adding more carbons.
Adding more carbons, how many?
3.
Let's try again.
I counted wrong.
Indeed.
2?
2 carbons, yeah. We're adding 2 carbons. So indeed, yeah, 2 carbons is what we're adding here. So, how might we add those 2 carbons?
I was gonna say stork, but never mind.
So stork is,
It's 1, 2, so I was just thinking.
yeah. So we're just adding 2 carbon. That's all we're doing. This one is simpler than I think you're thinking, if that makes sense. There is a reagent that you just add however many carbons to a Michael acceptor.
Is it acetoacetate?
The acetoacetate synthesis, there's an easier way to go about this. The acetoacetate, that one does add alkyl groups, yes, but there's an easier way to get this one done.
Could you do ethyl MGBr?
Not that one, but you're very close. Ethyl MGBr would attack the carbonyl, right? Because ethyl is not a Michael donor, but we have a Grignard is not a Michael donor, but what is a Michael donor?
Gilman?
Gilman, right. So instead, this thing will get us where we need to go. Gilman will attack position. It'll do a 1-4 addition. Remember, a Grignard will do a 1-2 addition, so it will add to your carbonyl. A Gilman reagent will add to your double bond instead. So that's the reagent we're looking for here, and then followed by acid. So that's... go ahead.
So under Michael addition, conjugate addition,
Right.
it's a Gilman.
Correct, yeah. So, because a Gilman reagent is a Michael donor. A Grignard is not. Just because the Gilman reagent is less reactive than the Grignard is. And we remember with Michael additions, we want them to be less reactive. So that will go for the conjugated position instead. All right, so that was using the ethyl Gilman reagent, followed by just a quick acid wash. So with the mechanism here we're looking at, there's our ethyl. It's going to go ahead and attack. Pop this open. And remember, we do have the option to do other alkylations if we are so inclined, because we now have an enolate just ready to go. But if we just need the alkane, or not alkane, but if we don't want to add any more stuff, then we just need to do an acid wash. That'll protonate this thing to give us the enol, which then will tautomerize to the ketone. So that's tautomerization for the last step there. Alright, so the trick here was to use the Gilman reagent to get this done. Okay, and we have one more to go. Alrighty. Now that we have our product, let's do one last thing with it. Oops. So here's our product. All right, so what have we done?
We've added a double bond on the alpha carbon.
And what does that mean then? Reaction-wise, what are we thinking?
I think we could maybe brominate it and then eliminate it to create a double bond there.
So that would work if we had a carbon there already. The problem is we do not have. If we had this molecule, yeah, we could brominate and eliminate. Yeah, that would make sense. But we do not have a methyl group there. I'll give you a hint, we did this one already in our synthesis of this molecule.
You add enolate with heat.
Okay. What else? That's 2 of the 3 things we need. Where's our carbon coming from?
Oh, formaldehyde?
Formaldehyde, right. So, it's just the same as before. So we need to take our formaldehyde, treat it with NaOH to do nothing at all, and then we slowly add in our ketone, and then heat it up. And poof, we will have now added a single carbon with a double bond onto our molecule. All right, so again, the alpha proton for our ketone will attack the formaldehyde. I mean, it's really exactly the same as this one. We attack the formaldehyde, and we end up with our beta hydroxy species, which then we will eliminate using heat, giving us the condensation product. Okay, so same mechanism here. So that's how we will accomplish that.
So what was this one called? To reference the note.
Oh, it's another mixed aldol.
Mixed alpha. Okay.
Mixed aldol condensation, I suppose. So, look at all the fun stuff we can do. So, I liked that problem. That was a fun one. Shall we do some more? Let's do something with... I know, let's do one of these. Yes. Okay, yeah. Okay, let's go with... any other questions on any of these, 5 or whatever reactions we just did on this molecule? Alrighty. Let's do the following then. Alright, make me this thing. Using any reagents you like. Let's figure out how to do it. Hopefully we can see what's the same and what's different between the starting material and the product. So, first question you want to ask yourself, besides what's different, is what's the type of functionalization here?
Is it an ester?
Is it a stork?
Not quite. I'll go with Narek's answer. And how did you know it was a stork?
1-5.
Yeah, it's 1-5, right? So the ester ones usually give you 1-3. So 1-5 is characteristic of a stork. So we have a carbonyl on position 1, a carbonyl on position 5. This is a stork enamine synthesis. And remember that a stork is essentially a Michael addition, except we're using a non-traditional Michael donor. So, because our cyclopentanone here does not have any other double bonds, it can't be the acceptor. It has to be the donor. So, with that, this is our Michael donor, which means that somewhere in this question mark of reagents, we have to have our Michael acceptor. And so our acceptor is going to be the rest of the molecule. And we just need to remember that the acceptor needs to be an alpha-beta unsaturated compound. So, how are we going to make all this work? How are we going to make this into a beta unsaturated, alpha-beta unsaturated compound? Or rather, what's the structure of that going to look like?
Is it just the same structure that's on it, but a double bond between 3 and 4?
Yeah, you're absolutely right. So, boom, boom. Oops, totally put an extra carbon here. Yes, this will be our Michael acceptor, therefore. So, remember, the bond is going to be formed between our alpha carbon and the double bond itself. So, as I've written, this will be 3, 4, and 5, right? 1 and 2 are part of your Michael donor. 3, 4, and 5 are part of your acceptor. And remember that it's always the double bond between 3 and 4. Absolutely right. So that's going to be our Michael acceptor. So the reaction conditions we're going to need, what are those going to be? What do we have to do first before we put in our Michael acceptor?
Deprotonate.
Not yet.
KH or LDA.
Not yet. Actually, we don't need it at all, in fact.
Use an amine?
Yeah, we need to do, since this is an enamine synthesis, we need to make the enamine. And so, specifically, Narek, what type of amine do we need?
I forgot the name, but it has 2 R groups.
2 R groups, yes.
Yeah.
So a secondary amine, yeah. Secondary amine acid, some heat maybe. That'll get us, that's going to take the place of our LDA or KH. Since this is not a typical Michael addition, we're going to, instead of deprotonating, we're going to form the enamine. And the enamine will already have our double bond there. So we actually do not need to make an enolate itself. From there, now we can put in our Michael acceptor. So we're going to have lone pair come down. This attacks. Opens this up. I have no space, as always. We have our imine, or iminium, I suppose, because it's charged. And now we're going to have the new bond that's being formed between our purple carbons. So those are our purple carbons. So now we just have to put everything else that's on them. So we now have our enolate, and again, if we were so inclined, we could put some other stuff on this, but we don't need to, so let's just go ahead and add our acid. Doing so will not only form the enolate on the enol on the right side, but it will also hydrolyze our imine, giving us now the enol technically, which then tautomerizes to form the ketone on the other side. Did I lose a carbon? I did. There we go. So our reagents would be, first reagent would be some secondary amine, acid, and heat. After that, we just need to do an acid wash, maybe some heat in there too, and we'll end up with our product. Alright, so let me make that big. So stork, you know there's gotta be a stork happening if it's a 1,5 product. And remember, with stork, you actually don't need the LDA or KH. We use an amine instead. And it's not actually acting as a base necessarily, it's going to be more a nucleophile. And the R groups, of course, can be methyls, ethyls, whatever. Just alkyl groups on the R. It has to be a secondary amine, of course, though.
Can you explain the step where it says H3O plus?
Yeah. So H3O plus is going to do two things. It's going to first deprotonate, or it's going to protonate this one. Right. Hopefully that's the easy part. With the remember that imines will hydrolyze to form ketones or aldehydes in the presence of acid. So remember that in the presence of acid, you'll just hydrolyze to the ketone or aldehyde. How that works, you end up protonating first. And then water can come in. Open it up. So you now have both the amine. Here, let me move it a little bit bigger. So we now have our amine and the water. We can go ahead and do a proton shift. And then close this down. And our amine can come in and grab proton, giving us the ketone at the end. So we can, that's all that's happening. So we're just hydrolyzing our imine, forming the ketone where that was.
Thank you.
Okay, cool. All right, and so, yeah, cool. All right, so our product is, go ahead, Eric, or whoever.
Oh, I was gonna say, are we missing one more thing in our answer? Like,
Are we?
step one is NH2 and then H plus E. Should we just write what we're adding onto, or what we're attacking?
Oh, yeah, good point. Yes, we are missing our carbon source. Yes. I guess so that'll be step 2, yeah. Step 2 will be this thing. And then step 3 then would be, yeah, the acid and heat. Yeah, good call. So the reagents necessary for this transformation are, from the cyclopentanone, were the following. Great. Good. So yeah, just remember stork gives you 1,5. So we'll just write them out again one more time. So if your product is 1,3, difunctionalized, this has got to be an aldol or a claisen. And so a 1,3 product might look like this. You know, throw as many R groups as you want on here. The point is that you have two functional groups that have a 1,3 relationship to each other. Those can be formed from an aldol or a claisen. And remember that within those we have the malonic ester or the acetic acetate synthesis. Those are both subdivisions of claisens, but those all give you 1,3 difunctionalized products. 1,4 additions come from Michael additions. Specifically, we're looking at conjugate addition. And that's going to be through your Gilman or Michael donors, other Michael donors attacking. And 1,5 is a stork. And technically a 1,2 is, that's just regular carbonyl attack. That would be like a Grignard. So it's a good thing to check your functionalization. What has happened across your molecule? Is it a 1,3 addition, a 1,4, a 1,5, or a 1,2? I guess I could have done that numerically, but whatever. Alrighty.
And then like so the 1,3 looks like that, and then is there a specific thing we should look for the others?
Oh yeah, so like a stork would be a 1,5, whatever. Here's some R groups. With Gilman, of course, you're just adding alkanes, alkyl groups. So we're just extending something. So you're looking for something that's alpha beta unsaturated, going to have now more carbons, however many there happen to be. That would be an example of a Michael addition with a Gilman reagent. You could also have a Michael addition, say between let's see, what can we put on here? I don't know. There's just so many you can have with all the different Michael donors. We'll just leave this as is. So those are just conjugate additions through Michael addition. And then the Grignard, those are... you're adding on to your carbonyl itself, so... I don't know, something like that. Pretty indicative of a Grignard. So you're adding something to carbon 1, something to add to the oxygen. You're adding an ethyl group, in this case, to carbon 1, and you're adding a hydrogen to oxygen 2. That would be a 1,2 addition.
Thank you. That's very helpful.
All right, so let's spend the last what do we have, like 20 minutes? Let's take a look, or 30 minutes rather. Let's take a look at some of these ACS problems. So those are in extra resources. If you just hop over there and click Enolate's ACS guide, I can copy it again, I suppose, or what I can... I can't reply to it. Whatever. Go ahead and download that. Let's open that up and let's look at some of these problems. So let's take a look at let's take a look at number 3 on the practice questions here. So I'm gonna move this over here, and I can actually switch my screen if that's easier for y'all. Okay. So let's take a look at number 3 here. So the question is, which of these is the product of an aldol condensation? And so with an aldol condensation, what are we looking for?
A13.
We're looking at a 1,3, and we're also looking at formation of a double bond, right? So 2 of these choices we can eliminate right away. And which 2 can we get rid of?
Possible? Can you zoom in a bit? Sorry.
Oh, yeah. Oh. Is this big enough?
Yeah, that's better.
Okay, I wonder if I can move this thing. I can. Okay, good. So, which 2 of these questions can we...
B and C.
B and C can get rid of.
Don't have the double bond.
Correct. Right. We don't have any double bonds to carbon, at least, in B and C, so we can get rid of those. So our choices then are A or D. And so we have to ask ourselves, so an aldol condensation is a 1,3 addition, right? Technically, we're putting our hydroxy on number 3, and then we're going to eliminate it. So the question is, are we eliminating on the side closer to the ketone or the side farther from the ketone? Because that's the difference between A and D, right? Is there's just which side are we eliminating from?
Farther from.
50% chance, and it's wrong. So it's the closer side, right? We always make an alpha-beta unsaturation with a condensation. So we lose the alpha proton, that's the most acidic one, and then our hydroxide gets kicked out as a leaving group. So because it's the alpha proton that's being removed, our new double bond is going to be formed between that alpha carbon and the carbon that had the hydroxy, which was carbon 3, or our beta carbon. So we're going to form our double bond between the alpha and beta positions, which will give us answer A here.
Professor, I had a quick question.
Yeah.
Wouldn't D technically be a 1,4? Or is that still a 1,3?
So, D would be, so we have carbon 1 as our carbonyl, 2, 3, 4. It could be either 3 or 4. This could be in addition to carbon 3, and we've eliminated this somehow on the other side. It's just unlikely to eliminate that direction, because if we look, an alpha proton is much more acidic than a gamma proton is. And so just equilibrium-wise, it's unlikely that we're going to eliminate that side. So we could classify D as a 1,3 addition as well. But the direct 1,3 addition is the hydroxy group. So we're technically forming... none of these are 1,3 additions anyway. But we're forming a hydroxy group, right? That's going to be on carbon 3. That's what gets eliminated. It's going to eliminate either between 2 and 3 or between 3 and 4. And it's always going to eliminate between 2 and 3 because carbon 2's proton is much more acidic than carbon 4's proton. All right. Let's look at, why don't we do number 4? So which set of reagents would accomplish this conversion? Oh god, I hate these structures so much. It looks like we have a diester and we are adding an alkyl group to that ester. So with this one, we have 4 options that seemingly are pretty okay. But hopefully we can figure out a couple of them just seem a little off. So what's happening here, of course, is we're going from our diester to now having 2 more carbons attached to the carbon in between the esters.
That should be.
Go ahead.
Is it B or D?
It is B or D. So let's look at why A and C are not the best here. If we use A, we deprotonate, form the enolate, right? And then we're adding ethanol in, and that's just going to do nothing, right? Ethanol is not an electrophile. There's no reason that an enolate would attack ethanol, so doesn't really make sense there, because we just don't have an electrophile. We have a nucleophile, but no electrophile. With C, again, we're going to have a nucleophile without an electrophile. We don't really ever see an alkene by itself being attacked by a nucleophile. So A and C kind of, yes, get rid of those. So, B or D, that's what it comes down to. So, let's take a look at them. If we do B, what's that first reagent do? What is that going to do to our compound?
Doesn't it just
deprotonate?
Okay. Yeah, deprotonates, right? Was that what you were going to say?
Yeah.
Cool. Yeah, so we deprotonate, and then we have, what's that second one going to do then? What is that acting as?
It's gonna attach the CH3 and CH2 and
Right,
take off
exactly. We're going to end up making the product that we're looking for here, because an alkyl halide is an electrophile. So our nucleophile that we formed by deprotonating our enolate, making the enolate as a nucleophile, attacks the alkyl halide, our electrophile, and now we have our added ethyl group on there. If we look at D, that has nothing to do with the alpha carbon. That's just going to hydrolyze these esters, but just remake them as ethyl esters anyway. So nothing's going to happen with D. So what we're looking for, the real difference here is 3 of these have bases, and only 1 has an electrophile in them. So we're looking here for B as our answer, because we need that base and we need an electrophile to add on to our alpha carbon. All right, so does that one make sense? All right, go ahead. No? Okay. Let's see, what shall we do? Reduce the reduction, okay, whatever. Let's see. All right, yeah, let's take a look at this. So we have number 8, but that's what we're looking at here. We have an aldehyde being treated with aqueous hydroxide. So what type of reaction are we looking at here? before we even look at the products? What type, just from the starting material and the reagents? Same thing.
Aldol.
We're looking at an aldol, right? And so this, because there's no other carbon-containing thing, this is just a two of the same molecule, aldol. So, aldols, remember, we're looking at 1,3 addition. And so, if we look at our answer choices, we have really only two options that are 1,3 addition. Because B, I don't even know what the hell B is doing, so doesn't really make sense to have B there, so we can just throw that out. D has 1, 2, 3, 4, 5. D has a 1,5 addition, so that's not right. So we need to look now between A and C. And so if we think about an aldol, remember that the word aldol is the name for the type of product you get. And so ald stands for aldehyde, ol stands for alcohol, and so if we're looking for something that has an aldehyde and alcohol in it, the only option is C, right? And we can also just remember that aldol gives us a beta hydroxy aldehyde, as opposed to a keto aldehyde. We could go from C to A by oxidizing, but the product itself from this set of reagents alone should be C. Right? We're looking at a 1,3 adding a hydroxy on there. All right, questions on that one?
So we could just cross out A and, well, first B, because...
Yeah, B makes absolutely no sense. Yeah.
And we could cross out A because it doesn't have the OH.
Yeah, you can cross that out, and then if you want to think about between C and D, you're looking at 1,4 or 1,5.
Right.
I'm sorry, 1,3 or 1,5. And so, yeah. Worst case, just do the mechanism and see what you get. So, without even looking at the choices. All right, so they like their mechanism questions too. So how about we look at number 9? Which of these is not a step in the mechanism of an aldol reaction? So if we look at A, what is A doing? We're going to look at all 4 of these, so and then we'll make our choice. What does A represent?
It's deprotonating the alpha proton.
Yeah, deprotes the alpha proton, forming the enolate, right? Is that something that we should expect in an aldol?
Yes.
Yeah, absolutely. So that's definitely good. How about B? What is B representing?
Is it the electrophile and nucleophile?
Yeah, right. So we have our enolate, the nucleophile, attacking the electrophile. Is that something that we're expecting in an aldol?
Yeah.
Yeah, for sure. Part C, what does that one represent?
Protonating.
Protonating. Is that something we see in aldol?
Yeah.
Yeah, it is, right? So there we go. D is the answer. But let's just make sure. So even though we eliminated the other 3, the other one, of course, makes no sense because we don't have an oxygen attacking. We're forming a carbon-carbon bond, not an oxygen-carbon bond here. So part D is the one that does not make sense. And that's not a step that we see in aldol. Alrighty. Let's see. Okay, how about we do number 12 now? So I'm going to move on this side. Which of these reactants can be used to make the compound shown by an intramolecular aldol reaction? So how are we going to split this thing up?
Should there be 6 carbons between, or I guess 4 carbons between 2 double bond O's?
One,
So it'd be a
two,
6.
three, 4. Yes, we are indeed seeing that. So the bond that's being broken is this double bond, right? Like if we were to just cleave that, that's where the reaction is taking place. So absolutely, we have our top carbon here. Go to the left, go to the bottom, go to the bottom, and then we have that. So we have 3 carbons in between our C double bond O's. So let's look at which answer choices have 3 carbons in between. It looks like option A has carbons in between, so we can keep that for now. 1, 2, 3. Option B also has 3 carbons in between. Option C only has 2 carbons in between, so that's out. And part D has 3 carbonyls, which makes no sense. So it's between A and B. And so now we just need to think, do we have an ethyl group and an aldehyde, or 2 methyl ketones? And so if we cleave that, if we cleave along this double bond here, we see that we do have 2 methyl ketones. Right, that this top right carbon is our alpha carbon. That one has attacked the other carbonyl, and so that must be a methyl group there, which means that option B is our answer. All right, that so far so good. Okay, let's take a look at this one. Which compound does not react with the iota form test? Do you remember haloform? The haloform reaction? You use sodium hydroxide and either bromine or iodine or chlorine. What does that haloform reaction do? What type of substrate do you need?
Is it a methyl
The
ketone?
methyl ketone, right. So methyl ketones will react to form a haloform. So which of these is not a methyl ketone?
B.
B, right. It's got ethyl groups only. All the other 3 here have CH3s as methyl groups. So A, B, and D are all methyl ketones, so they would undergo this reaction, but the ethyl one would not. Alrighty, let's do... Alright, let's see here. Okay. 14. Which of these compounds cannot undergo an aldol reaction in the presence of dilute base?
So what does dilute base really mean?
NaOH and water. Yeah.
Okay.
Is it A?
Nope.
Mm.
What's your rationale for?
Because it doesn't have any alpha.
Yeah,
Alpha hydrogen.
Ramon's actually absolutely right. Yeah, no alpha protons on B, so can't do anything. What made you say A out of curiosity?
The C6H4.
Okay, that's just a benzene. I hate the way they do this, but yeah, that's a benzene. So
Okay.
yeah, I know it's weird to see it that way. Yeah. So Ramon has the right answer. That B does not have any alpha protons, and since there's no other substrate here, these ones will all be able to react with themselves, right? So because all of these have alpha protons, so they would be able to react with themselves through aldol, but B does not, so it cannot react with itself. Alrighty, so how about 15? Which set of reactants, in the presence of a basic catalyst, can be used to prepare this compound? So this compound is an alpha-beta unsaturated ketone, which tells us what type of reaction is this going to be, and then we'll figure this out after. What type of reaction gives us a a alpha-beta unsaturated carbonyl? Yeah, it's an aldol condensation. So we're looking at something that will give us an aldol condensation here. So hopefully we can eliminate 2 of these right off the bat. Which 2 do not make sense as an aldol condensation?
D.
Yeah, D absolutely is the worst of all. Yeah, D is, we're not adding benzene to some random ketone. That's definitely not going to happen. Alright, so that's 1 down. What else do we have? Which one?
B.
B is also, yeah, makes no sense, right? We're not going to add an alkyl halide to this. That doesn't make sense. So, A or C, it's coming down to. And so, if we look here, the only difference between A and C is we just have 1 more carbon in C on the second compound. So it's simply a matter of counting carbons, I suppose. So,
C.
it's going to be C, right? Yeah, exactly. So, if you count the carbons in A, you have 6 on the benzene, and then 3 more will give you 9. In this final product, you have 6, 7, 8, 9, 10. So you're missing a carbon if you do A. So it's got to be C. Nice. Okay. 1 more. Let's do a good one. Alright, here we go. This is an interesting one. So we have an enolate type reaction here.
Sorry, which one are we
23,
looking at?
yeah, I'm sorry. I forgot. My screen sharing one is only on 23, but y'all are seeing the whole thing. Yeah, so 23, what is the product of this reaction? We have the formal furan and nitromethane in the presence of a base. So, which of these 2 compounds has something for the base to react with?
The CH3 and
Yeah, the nitromethane is the one that we're going to be putting our base with. So we're going to form a kind of a fake enolate, right? It's not necessarily an enolate specifically, but it's going to have a stabilized anion. We're going to deprotonate that, and it'll be stabilized by the nitro group withdrawing electron density. So if that's going to be the one reacting with the base, that's our nucleophile then. Where is that nucleophile going to attack? What's the most electrophilic position on this thing here?
Aldehyde.
The aldehyde, right. And so, which one of these, therefore, has the connection between the aldehyde and the nitromethane? So treat this just as if you would in aldol.
So is it D?
D, not quite. Aldols do not give us... so remember, the electrophile in the aldol becomes the hydroxide, not a carbonyl. So we're actually looking at C here. So we're going to form a hydroxide there, and it's going to be condensed. We're going to condense that, do an aldol condensation type thing on C. B, of course, makes no sense. So we're missing a carbon if we do B, so let's not even worry about that. Part D, what we make is we make the COH instead of C double bond O, but we're condensing it, so we're going to form a double bond instead. So the either options, we're going to form the double bond C double bond C, or we're going to form a hydroxide. And since hydroxide is not one of the options we have here, it's got to be a condensation instead. So C is our answer. A is not the answer, by the way. I guess this doesn't even make sense because we don't have the right amount of carbons, but this is not going to be a conjugate addition because you need 2 electron withdrawing groups for this to act as a Michael donor. So we're not going to have a Michael addition happening here. Only this is a regular 1-2 addition to our like as if this was a Grignard, basically. Okay, we're out of time, so that's it for today. Wednesday we'll start talking about amino acids. Remember, of course, amino acids are not on your exam. The exam is Thursday at whatever time it's going to be. Yeah, I guess Wednesday, just let me know how many presentations are still left, and we'll figure out the time. And so Wednesday we'll talk about amino acids. Okay, cool. So that's it.